Suppose you throw a die infinitely often. What is the chance that the face shows a 6 infinitely often? I'll let you think about this problem for a while. The probability should equal 1. And why is it so? You can think about it naively as follows. Suppose the probability is strictly less than 1. What will happen? Naively, this means it is not the case that when you throw a die infinitely often, then you get a 6 infinitely often. And that situation means that you will only get a 6 finitely often. And that further means that after some point, you will only get the face showing 1 through 5. Well, that shouldn't happen, right? Otherwise, the casinos will get into big troubles. If you throw a die after finitely many times, you only get 1 through 5 and there are no 6. That is too crazy. But this explanation is not very rigorous. In order to make this problem rigorous, we need to introduce a very powerful theorem called the Borel Cantelli lemma. So let's get started. The Borel Cantelli lemma states the following. Let A1, A2, be events and define A star to be the lim sup of the sequence of events A sub n as n go to infinity. Remember, this means the intersection of the union of A sub n's, where this intersection is from a capital N equal to 1 to infinity, and this union is from little n equal to capital N to infinity. So you probably know this from the measure theory, but let me still recall it. Then, the Borel Cantelli lemma says we will have the following. First, if you sum up those probabilities from n equal to 1 to infinity, and if you get a finite number for the sum of all those probabilities, then the probability of the event A star is equal to 0. Remember, the meaning of A star in probability theory means that those sequence of events will happen infinitely often. Namely, if your probability space is X, B, P, where X is a space of points and B is a sigma algebra and the P is a probability here, given any point, say little x in capital X, that point lives in A star means that for any n greater or equal to 1, there always exists a little n greater or equal to capital N such that that point lives in An. That's the meaning of intersection and union. And the probability of A star is equal to 0 means that it is impossible for those events to happen infinite often. So that is the first part of the Borel Cantelli lemma. Now here's the second part, which is some sort of the converse of the first part. So what will happen if you get this sum equal to infinity? So if the sum of those events' probability is equal to infinity, what do you think that the result will be? So what is the probability of A star in this case? I'll let you think about it for a while. Some of you may think, oh well, so now in this case, if the sum of the probabilities is equal to infinity, the probability of this should be greater than 0. But if you think about this carefully, is it correct? The answer is no. Because for example, you can take this probability space to be, the space is the interval from 0 to 1, and the sigma algebra is the Borel sigma algebra on 0 to 1 with the Euro topology, and the probability is the Lebesgue measure on 0, 1. And you take A sub n to the interval from 1 minus 1 over n to 1. It follows that A star, which is intersection from n equal to 1 to infinity of the union when n is from capital N to infinity of A sub n is equal to the intersection of capital N from n equal to 1 to infinity of the interval from 1 minus 1 over n, capital N, to 1 is equal to the singleton 1. So the probability of A star is equal to 0 because the Lebesgue measure of the singleton is 0. But at the same time, if you take the sum of the probability of all those A sub n's, what will you get? What you get is the summation of 1 over n from n equal to 1 to infinity, which is infinity. So, although you have a summation equal to infinity, you still get the probability 0. So, this is not necessarily greater than 0. It could be equal to 0, even if the summation of the probabilities is equal to infinity. Okay, so this possible answer is wrong. It seems that if the summation of the probabilities is equal to infinity, then you won't get anything interesting just from this condition alone. So maybe it will be interesting if we add something that is more interesting to here. So, what condition do we want to add to this? What would be a very natural condition for any statement in probability theory? So look at here. We have a sequence of events. what condition that is so natural to put on those sequence of events. You should be able to come up with an answer immediately. That is, if you further assume that those events are independent, then what are we going to get? Well, this time, this answer will be not so trivial. You can take a very wild guess, but I should expect you to get the correct answer. That is because of the problem we talked about at the beginning. This should give you a hint what this probability should be. It should be just 1. Does this result look surprising to you? If the sequence of events are independent, then the probability of the event that happens infinitely often will either be 0 or 1. Isn't that surprising? Actually, the Borel Cantelli lemma is just one of many theorems in mathematics on the so-called 0-1 law. There are many 0-1 laws in mathematics, and the Borel Cantelli lemma may be the easiest one of them. And the 0-1 law is again a special case in mathematics on the so-called the phenomenon of dichotomy, which says in mathematics, although you really expect there are many cases to happen, in the end you will only get 2 special cases. Either this or that will happen. That is kind of surprising, but there will be some intrinsic reason behind that, as we will see in the following proof of the Borel Cantelli lemma. And now let me talk about the proof.